Now that we've discussed forces in general, and the basic concept of what force is, it becomes important to understand the different types of forces that you will experience or that we experience on a fairly regular basis. Uh, we call them common forces. They may be referred to as everyday forces. But you just need to understand that these are the forces that impact your life essentially at every moment that you're alive. There's five that we're going to discuss in this course for now. The first being weight, which is the force due to gravity. The second being the normal force, and we'll get to a more textbook definition of what normal means in normal force. We also have tension, friction, and the applied force. Some of these you may already be aware of, some of them you may not, and we're going to try and clarify that by the end of this video. The important thing for now, moving forward, is since all of these are types of forces, therefore they must be measured in newtons. They are absolutely the same in terms of the fact that they are forces. They are just different. They are applied to objects due to different causes. We take a look at the first, which would be the force of gravity, also known as weight. We represent that with a capital F and a sub G, so the force of gravity. You'll remember from Newton's second law that F equals ma. Therefore, the force of gravity should equal the mass of the object times that acceleration due to gravity. So you can still see here that F equals ma. We just replaced a with lowercase g because it's the acceleration due to gravity. Now the mass of an object will not change. That's the amount of matter it's made up of. But the acceleration due to gravity may change based on where you're located. For example, if you're on Earth, the acceleration is negative 9.81 meters per second squared. So you will have a particular weight based on your mass, based on the gravity of Earth. If you were, however, to travel to the moon, which has an acceleration due to gravity of roughly negative 1.67 meters per second squared, your weight would be about 1/6 what it is on Earth because the acceleration of gravity on the moon is about 1/6 that of Earth. Going the other way, if you were to go to Jupiter, which is extremely, extremely massive compared to both Earth and the moon, your mass would be pulled down at an acceleration of about negative 25.94, so roughly about negative 26 meters per second squared. So you can therefore figure that your weight on Jupiter would be significantly more, about 2.5 times, a little over 2.5 times more than it would be on Earth. If you weighed 100 pounds on Earth, just by simply going to Jupiter, you would now weigh about 250, more about 260 pounds. The next force we're going to talk about is the normal force. And one thing to note here, normal does not mean like this force is pretty okay, he's not strange, I'm going to hang out with him. Normal in this case, you have to go back to like math class. Normal is another way of saying perpendicular. If something is normal to another surface, it is perpendicular to that surface. The normal force is represented by a capital F and a sub n, so the normal force, and it's essentially any force from a surface that acts perpendicular to that object. This is a little bit easier to see with a drawing or diagram, so I will show that down here in this example. But the one thing to note right now, normal just means perpendicular. So if you have a surface here, normal to that surface would be anything that is perpendicular. So if we take a look at this example here, we have an object that's resting on the table. We know that gravity pulls the object down into the table based on the force of weight. We also know from Newton's third law that if the block pushes on the table must therefore push on the block. So if we take a look at the normal force acting on this object right here, it's the force from this surface, the table, that acts perpendicular. So the normal force would act perpendicular in this direction. And if I extend this line down just to show you, you should be able to see that that is perpendicular to the surface. Normal force just acts perpendicular to the surface. It does not matter about the orientation of that surface. As an example of that statement, if you were to have an object that's resting on a ramp, yes, gravity is trying to pull this object down towards Earth, but the normal force from this table, remember, if the block pushes the table pushes the block, but normal is perpendicular. So many students seem to think that your normal force should go here, but if you take a look, this is not normal or perpendicular to this surface, so that would be absolutely wrong. So if we back that up, that would be the incorrect labeling of the normal force. If we want to look at the correct labeling of the normal force, you would have to draw a normal force such as this, and as you can see when I extend this down, This is the normal force as it is perpendicular to the surface with which is applying that force. So remember, normal is just perpendicular. The next force we're going to discuss is going to be the force of tension. You guys are probably used to some tension. It's just any force exerted by the pull of a string, a chain, etc. It's represented by a capital F and a sub T. To show you an example here, since I feel many of you probably already know this, if you have a rope and you have an object or a mass hanging from that rope, well, the force of tension is very simply going to be the force with which that rope is pulling up. We know gravity will pull down, so your force of gravity would be here. The force of tension is what's resisting that pull of gravity, which is what allows this rope to this mass to hang here. If we were to take a look at a second example, where I have two strings now at an angle, it's really no different. You just have to pay attention to your geometry. Here's my object. I have the force of tension from rope number 1. I also have the force of tension from rope number 2. So just realize right now that the force of tension is just any force exerted by the pull of a string, a chain, or anything like that. The next force we're going to discuss is known as the force of friction. I think many people conceptually understand friction. They may not understand where it comes from, however. Force of friction represented by a capital F sub lowercase f, and it's very simply the force due to imperfections in the surfaces between two objects. If we take a look at our example, we have a block resting on a table. Looks like this is fairly flat, so you would expect there to not be any friction. However, if we magnify this, we should be able to see that the bottom of our block under a microscope would look more like this. Nothing is going to be perfect. As human beings, we have not developed anything that will create a completely imperfection-free surface. If we take a look at the table, you will also notice that that is not perfect as well. And due to these imperfections, when these two are resting on one another, what you will wind up getting is something that looks a little bit more like this. And as you can see, these different imperfections begin to lock into one another. Therefore, if I try to move or slide one of these objects on the other, you'll notice that there will be some points of contact where you will have some resistance force generated. So that's where this friction comes from. It comes from these imperfections kind of interlocking with one another. They exert a force wherever they're going to wind up touching one another. And that's what results in this frictional force. Now, the big important key with friction is that the force of friction will always, always, always oppose or act in the opposite direction of the motion of the object. It will always act in the opposite direction. Friction will never push an object forward. It will only resist the motion of that object. So it always acts in the opposite direction of motion. Right? If friction were to push in the same direction as motion, that would mean that if you push an object and stops pushing it, friction would continue to push it forward. It would accelerate exponentially until it, crashed into something and physics is broken. So just be aware, it always, always, always acts in the opposite direction. This brings us to our last force, the applied force. There tends to be a lot of confusion about the applied force, but I've tried to rework the definition of it so it maybe makes a little bit more sense. The applied force is represented by a capital F and a sub A. The applied force is basically the general term for any force that doesn't fit into one of these categories that we've already spoken about. That's not an exact definition, but for now, it's the general term. If it's not the force of gravity, which is weight, if it's not the normal force, the force of tension, or the force of friction, it's some kind of force that's being applied to an object from some kind of outside object, maybe a person, maybe a car, as you'll see in these examples. But if we take a look here, you have a person pushing on this box. Now, just to kind of bring everything together, we know this box will have the force of gravity. We know that the ground will push back up, which gives us the normal force. We know that if this object is trying to be moved, that it's going to resist that motion, and you will have some kind of frictional force here as well. But the person is also pushing on this object. That's not tension, it's not gravity, it's not friction, it's certainly not the normal force. So this is where we're going to come up with this applied force. This person is applying some kind of force to this object, and it doesn't really fit into one of these other categories. Likewise, if we take a look at this object over here, again, we know that gravity pulls this object down, which will give it some weight. We know that the road will also push up on this object, which will provide a normal force, which will be perpendicular or normal to this surface. We also know that as the car hits that box, it's going to start to move. And when it's moving in this direction, to the right, the frictional force between the road and the surface of that box will act to the left. But again, this car has hit this object. It's clearly exerting a force. It's bringing this to motion, so there's a change in motion. The question is, what would that force be? Well, that force in this case must be the applied force.